Great. Well, welcome everyone to this third edition of our Quantum Energy Initiative YouTube seminar. So as always, I present a bit the QEI before we start. So Quantum Energy Initiative is an initiative started a year ago, whose goal is to gather experts and raise awareness towards the energy consumption of quantum technologies. We believe that it's important to look at these problems now at the early stage of the development of these technologies, because we still have a lot of power to influence decisions and what hardware will be used. And in this context, we're organizing this series of seminars that are all online and all recorded. We recently also had a workshop in Singapore that went really well. You can see all the videos of our YouTube channel. And today it's my great pleasure to welcome Alhun Aydin, who I met precisely in this workshop. He's now an associate professor right in Sabancı University in Istanbul. Previously postdoc at Harvard, still affiliated there. He started a group that is beautifully called Quantum Energy Research Group. So we figured that it was a good idea to invite him here, and so he can let us know what they are working on there. And Alhun, the floor is yours.
Thank you so much, Raja, for the introduction, and I'm glad to be part of this beautiful community, Quantum Energy Initiative. So yes, I kind of like borrowed the name of my research group. Okay, it's partly borrowed. I was already planning that because the research group of my PhD advisor was called actually Nano Energy Research Group. So I was already planning maybe I can form a quantum energy research group, but definitely the encouragement, I think, came after I see the initiative. So I can definitely say that the initiative is one of the reasons why I picked that name. So yes, I became a recent faculty member at Sabancı University and still affiliated with Harvard as an associate in the physics department. So today I will talk about a concept called non-uniform level scaling, and what we can, how we can use it in quantum energy devices. So first of all, with very briefly, I want to mention my research topics in our research group. So I divided into 3 teams, but in the end, they are more or less interconnected. So the first one is the theory of quantum materials, specifically the strange metals. With Heller group at Harvard, we are proposing a new framework to look at things and possibly solve some of the mysteries around the strange metals. The second theme is quantum thermodynamics and transport, which is actually my PhD topic. And thirdly, we are planning to apply this into some energy devices, like energy conversion, storage, and those type of devices. So you can reach out the website from this link. Okay, so today I would like to bring your attention to finite size systems. And here by finite size, I don't mean the number of constituents. I literally mean the spatial, the physical space is confined. We know it from, for example, actually this is very, very popular right now because of the Nobel Prize in chemistry of this year is given to the quantum dots. So I'm actually talking about those kind of systems, lower dimensional quantum confined systems, like thin films, wires, dots, and so on. So the important property of these materials, these materials are coming from the energy quantization. So the energy spectrum, the discreteness of the energy spectrum is very important in determining the physical properties of these materials. For example, one of the primary consequences is the density of states can change dramatically, and so on. So how these quantum the discreteness appears is the fact that these systems are so small that their sizes are comparable to the thermal de Broglie wavelengths of particles that are confined within. And that leads to important changes. For example, if you look at the system at thermal, for example, you see here the thermal population. It's basically Boltzmann factor here that I'm showing you. When you shrink the sizes of your system into very small scales, the discreteness become more apparent, and you see that ground and low-lying states determine the whole behavior of the system. So you can no longer treat the material as a bulk material. And this is one of the primary reasons why these geometry different, the confinement in different dimensions, and also the geometry of the confining system becomes very important. In particular, even at equilibrium, you can define, for example, any physical property. You can, for example, think of free energy in your system. It's a thermodynamic property, and it's no longer defined by the classical term, which was in textbooks. For example, you can see that, which is a result of a continuum approximation. Okay, so in textbooks, all the equations we see are derived based on the continuum approximation. You replace the summations with integrals. But once you do not do that at nanoscale, for example, the surface area, peripheral lengths, and number of vertices, the lower dimensional size variables, become also important. And we call them quantum size effects. So you need these effects in order to describe the, for example, free energy of a system properly at those scales. Okay, so these are known. Now I would like to bring your attention more into the geometry of the system. So here we will talk about something called size invariance. In order to do that, let's first define what do we mean by size, right? So sizes in mathematics, in measure theory, defined by Lebesgue measure. So there's a well-defined definition of what size is in mathematics. And it's basically, you can think of this cube, for example. It has one bulk size, which is its volume basically, and three lower dimensional size variables. Its surface areas, you can think of it as a two-dimensional size variable, peripheral lengths, one-dimensional size variable, and the number of vertices we call, these are basically the discontinuities in these 1D lines, right? So it's basically corners of this cube. So by using these four parameters, or four different numbers, for example, in this case, you can define the size of this object fully. And also the number of holes could be important if there are holes in your domain. So when we call size invariance, we are actually talking about not changing any of these parameters, so keeping all of these parameters constant. Now a question comes. Can we change the shape of an object without changing any of the size variables? Let's break down the question into a simple one. For example, we can do this, right? Take this sphere and also the cylinder. We can precisely make them having the same volume, right? We can equate the volume expressions and find the correct parameters so that they can give the same volume. But if you calculate the surface areas, those will be different in these objects. So what I'm talking about here is, let's keep all of these size variables constant, not just volume, surface area, peripheral length, number of vertices, and number of holes in your system. So can we do that? Can we keep these variables constant and change the shape of a domain? It turns out that we call it size-invariant shape transformation. By using this geometric technique, we can do this. And it is actually a very simple technique. For example, let's focus on this 2D example, 2D translational size-invariant shape transformation. Let's consider this as our initial domain, a circle in a disk inside the disk, a concentric disks. So this blue region is the region that I am interested in. You can, for example, think of these as two materials, but the electrons are confined in this region, denoted by the blue color. Okay. Now consider that I'm moving this inner disk somewhere inside the domain. So I'm translating it. And I'm reaching this final configuration. Now compare this initial and final configurations. What do you see? So their shapes are clearly different, right? Consider yourself, for example, an electron traveling in this domain. It's quite different from traveling in this donut shape, right? So the shapes are clearly different. But consider the size variables now. We don't have volume here. It's 2D. So the bulk variable is the surface area. So the surface area didn't change. We haven't removed anything from the domain, or we haven't added anything. The removed part was already there inside the domain. We just moved it inside the domain. And the peripheries are also the same. And we don't have any discontinuities in 1D in this case. So this is a size-invariant shape transformation. And you can do this also by rotating the object. So you can basically define infinitely many shapes by considering this technique. So the 1D version of this, it turns out that you can do this also in 1D, is just a flat bottom double well, right? So you have, so the boundary conditions are Dirichlet, by the way. I didn't tell you, but it doesn't have to be. But if it's Dirichlet boundary conditions, the effect is, of course, much more prominent. So you can think of this as a flat bottom double well, and changing this inner boundary, the location of this inner boundary cause the same effect. Okay, so you can consider this in any finite size systems. Let's say you have some Hamiltonian. It doesn't have to be this simple. You can also have interactions here and so on. But let's consider the free kinetic part and plus the potential part. Inside the domain blue region, we have zero potential for simplicity. And outside the white regions here have the infinite potential. Okay. So the key point here is, as you see, we have separated quantum size and shape effects. Now we can only focus on the effect of shape, changing the shape of the domain, how it affects the physical properties. So the quantum size effects will be constant in all of these domains. So you will see in the next slides that this leads to some very interesting effects in thermodynamics. Before that, I would like to also emphasize one important property of quantum shape effect. It's really a quantum effect because it comes from the quantum confinement. So you can't do this in, for example, in your room, right? If you have, let's say you took some square and you confine the gas in it at room temperature in your room scales, you won't observe these effects because this is strictly a quantum effect. You can see that, for example, if you calculate the quantum thermal density. So this is just telling you that how, if you look at things at thermal equilibrium, what would be the density of the particles inside your domain? It will be non-uniform, right? Because of the Dirichlet boundary conditions and wave nature of the particles, at such these confinements, for example, 20 nanometer was chosen as the length of this box. You see that the density goes to 0 near to the boundaries, and the particles, the density of the particles actually maximum where you are the most distant from any boundary inside your domain, right? So this is a quantum effect. If you remove the size square from here, you won't see this effect. So of course, it will be the constant throughout the domain. And this effect disappears when you increase the size of your domain. Let's say you tripled, you see the boundary layer becomes smaller, as you see here. And if you enlarge your domain, as you see, it becomes more and more uniform, the density of the particles. So it reaches to the classical uniform density in the limit of L goes to infinity. So you can also see that, for example, we have predicted these effects also analytically. And there, if you let h bar go to 0, all these quantum shape effect terms will disappear. And you will recover the classical limit. Okay, so after this introduction of this size-invariant shape transformation and quantum shape effects, let's talk about how these operations that we newly defined affect the spectrum of the system. So let's look at the level scaling. I will stick myself to the 1D example for simplicity. Let's say this is my domain. This is a 1D domain with Dirichlet boundary conditions here. And these are the momentum states. Again, I could give the energy states, but it scales with L squared, 1 over L squared, so it would be harder to follow. So I just picked the momentum states, okay? Now let's consider that I'm shrinking this domain. And how energy levels behave? Of course, the levels between the different momentums will increase because the confinement is increased, the domain sizes become small. But you see that this this increase in level spacing is uniform. It is the same for all states. Let's consider the left one here, starting one is the ground state, for example. The scaling is uniform, as you see. And it turns out that except some really mode-dependent manipulations in your system, and which you can't do actually in equilibrium cases, of course, well, this is almost always the case. You always have uniform level scaling. For example, you applied some electric field, the energy levels will just shift, and all of them will shift almost the same amount. And if you change the geometry of your system, if you change most of the things, so most of the cases, the level scaling will be uniform. But look what happens when we change, when we do this size-invariant shape transformation. So this was the boundary of our domain, and I'm changing its location inside the domain. And looking at the spectrum of this system, you see how almost chaotically it changes. The scalings are non-uniform, which means the ground state, first excited state, and other excited states behave completely differently with respect to each other. So this is what we mean by when we say non-uniform level scaling. And this is actually a continuous and global way to cause these changes in the spectra. You can do this continuously, and it is a global operation. It's not a mode-dependent operation. So in a recent article, I analyzed the spectrum due to this, how spectrum changes under this non-uniform level scaling. What I realized is the ground state reduces in the direction of increasing quantum shape effects. So the last thing that I told you might not tell you something like, so I haven't explained how you increase, for example, quantum shape effects, but due to the limited time, unfortunately, I can't do that. But let's consider that I picked some direction which denotes the increase in quantum shape effects, okay? And in that direction, when you do this operation, ground state always reduces. This is the first important observation. And the second important observation is the level splitting or degeneracy formation depending on the symmetries of the domain. So it's really depending on the symmetry of the geometry of your domain, either you induce level splitting or you induce degeneracy formation. For example, in this particular case, you basically induce fourfold degeneracy when you do this transformation from here to here. Okay, now we have looked at what non-uniform level scaling is and how it changes the spectra. Now let's consider the consequences in thermodynamic properties. As I told you before, we are interested in quasistatic changes. So these changes that we do in the system are infinitely slow, and we are always in contact with some heat bath at temperature T. So our density matrix is basically diagonal, and this is how we calculate partition function, free energy, entropy, and internal energy, basically standard statistical mechanical framework. So this is for a single particle. Of course, you can do this for n particle. The formalism would be the same. And okay, so this is the results for these 4 different thermodynamic property. The first one here, Z, is the partition function. It increases. So it tells you that there are more available space inside the domain. So this is really counterintuitive if you think about it, because we didn't change the volume or any other size variable. So effectively, there are more available states if you transition from 0-degree configuration, the left one, to 45-degree configuration. So that this right one is something in between, but the 45-degree one would be something like a diamond, right? So it really tells you that there is some effective volume which is increasing. Okay, now let's look at the free energy. So free energy decreases. So what free energy tells us? It tells us the direction of the spontaneous thermodynamic transition, right? If free energy decreases to some when under some operation, then this tells you that if you let the system alone, it will just transition into the lowest free energy state. Okay, but look at entropy now. In usual systems, in classical systems, we would expect free energy and entropy to behave oppositely, right? The systems try to minimize their free energy, and also this corresponds to the maximization of entropy. But here, you see something different. Entropy also decreases. So this is quite striking. Of course, everything is consistent. If you look at, for example, internal energy decreases so much that it compensates the decrease in both free energy and entropy. Okay, this is just a kind of a circular way of explaining this, but I can assure you that there are 2 more different ways to explain this, and they're one of the most fundamental one is in this article that I recently published. I encourage you to check this article to understand more about it, but I will also tell you in this presentation more about it, so don't worry. So, okay, so this is something classically impossible, unless you are talking about open systems. In open systems, of course, these such things could occur. But here we have, okay, here we don't have also an isolated system, so we are still in contact with heat bath, but still we have some counterintuitive behavior in the thermodynamic properties. And one of the, for example, implications of this, we can compare the isothermal expansion process in different systems. For example, in this A, you see the expansion of a classical gas, isothermal expansion. So what you expect, so these are blue, red, and green ones are free energy, entropy, and internal energy. So internal energy stays constant, it doesn't change. And entropy and free energy behaves oppositely. Free energy decreases, of course, when the gas expands, and entropy increases because there are more available states. Okay, if you look at the expansion of a quantum gas, where it is basically a confined gas, so there are quantum size effects involved, the situation is more or less similar, except there is also a decrease in internal energy. So this is known. This is not a very surprising result, but the surprising result is the last one. Effective expansion of a quantum gas due to this size-invariant shape transformation leads to the decrease of all three quantities. Now maybe you see more clear that internal energy compensates the decrease in free energy and entropy as it should, right? Because of the first law of thermodynamics. And also don't worry about the second law of thermodynamics. Everything is consistent with the thermodynamics here because we are in contact with heat bath. Don't forget that. So if you look at the total entropy of the system, it's constant. So this is a reversible process. There is no dissipation. Okay, so this is a quasistatic process, right? This is that's what I told you first. So the entropy of the combined system stays constant, but still the decrease in entropy while decreasing free energy in the system that you're considering is really striking. Okay, now maybe I can convince you why this actually happens and should happen actually. So let's consider the 1D system again. It's the simplest one. And let's investigate each eigenstate and each eigenfunction, how they behave. So let's look at the first 4 eigenstates and eigenfunctions. So L here is the position of this boundary here. So this has length 10. And 5 is the boundary is at the center of this thing. Okay, let's look at the first eigenfunction, the ground state. When you move the boundary to the right, you see that first eigenfunction extends. So it becomes larger, it occupies the ground state of the this entire domain, as it should. And look at what happens, the ground state decreases steadily. Okay, this is not unusual. But look at what happens to the first excited state. So initially, we have degeneracy at this center configuration. We have degeneracy between the ground state and the first excited state. In this case, they're the same states. And once you start to move this boundary to the right, you see that the first excited state actually shrinks here. It shrinks until it sees that, wait, I don't have to shrink to the right side of the domain. There is a more favorable state on the left side. So left side energy is less right now. So let me explain this again. So instead of being the ground state, occupying the ground state of the right side of this domain, it actually transitions into the first excited state of the left side of the domain. It is more favorable energetically, and it continues to expand after that. So you see that also you see this behavior also in the eigenstate. So it initially increases, this is the y-axis, by the way, the energy. So the energy actually increases first because of the shrinkage of this wave function. After, at this exact point, which is basically an avoided crossing, in this case, it's infinitesimally avoided because the domain has the Dirichlet boundary conditions. If you have like a finite boundaries, this will be a real avoided crossing. And it crosses into the other behavior, spread behavior. And what this tells you? So normally, from an expanding domain, we would expect the spread of the wave functions. So this spread behavior of ground state and other states are actually what we expect classically. But these shrinkages, those are the ones that causing these weird behaviors in entropy. Because look at what happens in the thermal probability, for example. So the thermal probability, because of this shrinkage, the first excited state, the thermal probability of first excited state decreases dramatically. And this leads to the increase of the ground state even more. So this is actually the reason why entropy becomes lower in this configuration. The particles, you know, the entropy is about the redistribution of the energy states of the populations in the energy states, right? So particles are actually favoring the ground state and low-lying states even more due to this operation. That's why the entropy decreases. And you see this also quantitatively if you look at energy per state. Look what happens, for example, here. The entropy follows the shrinkage paths. So these are the shrinkage paths. This is the shrinkage of the first excited state. This is the shrinkage of the second excited state, this one, and so on. So, and this is the total entropy. So you see that the black one, the total entropy, actually can be understood when you look at entropy per state and where the entropy decreases due to these shrinkages. So this is the effect that I called quantum thermal avalanche, because this is really a rush into ground state because of the geometric effects that you induce in your system. I don't know if this was clear, but I hope I explained it. But of course, if you have questions, you can ask about it. But yeah, this is the essence of the effect and one of the explanations of one of the striking consequences. And now I would like to mention some of the applications of this in quantum energy devices. The first application is designing a quantum heat engine based on this effect, this quantum shape effect in general we call. So here you see a Stirling-like cycle. I'm saying Stirling-like because, as you see, I changed one of the processes here. So in Stirling, we have isochoric and isothermal processes, right? Here, from first configuration to the second configuration, I'm keeping my volume constant, but also shape is also constant. So that's why we call it isoformal process. So it not only preserves the sizes, but also preserves the shape of the domain. So let me run by this to you. So this first configuration is in contact with cold bath and prepared at 45-degree angle. So first I'm giving some heat to the system and increasing the temperature of the heat bath and the system. And then I'm performing rotation. So I give work to the system, and from 45-degree configuration, I reach to the 0-degree configuration. Interesting thing here is from 2 to 3, while giving work, I also need to give heat to the system. So this is interesting. In classical Stirling cycle, the work and heat exchange are opposite. When you give work, you take heat from the system, and vice versa. So this is one of the interesting things, and this implies that you can induce cooling effect by compressing the system, at least effectively compressing the system. So this is really interesting, right? So when you compress a gas, its temperature increases. Here, its temperature decreases, so that you need to give also heat so that you can keep it at the same temperature with the heat bath. And from this configuration, 3 to 4, you are removing heat from the system, and you reach in this fourth configuration where you have 0-degree configuration in contact with cold bath. Now, this thing rotates from 0-degree to 45-degree spontaneously and you extract work from this rotation. And also, again, consistently with this formalism, you have also here the heat removal at the same time. So there are few important changes compared to classical Stirling cycle in this case. One is, as I told you, the work and heat outputs are actually have the same sign. Secondly, you may have noticed this, like we are taking the work out of system at the cold side of the cycle. In classical cycles, we are taking the work out in the hot side, right? That's where it has more pressure and so on. But here, this is because this is a quantum effect and it is enhanced at colder temperatures, we get work output at the cold side. And you can see also this from the TS and tau theta diagrams. So instead of PV diagram, we have tau theta diagram because we have not volumetric change, but some rotational change here. So we have torque and also the angle. And you see that in this tau theta diagram, the area under the cold, under this cold side is much larger than the hot side. So that also is in line with what I say. So this is one of the interesting cycles that you can design based on this. There is also an Otto version of this. The second example I would like to show you as an application is in thermoelectric devices. So in usual thermoelectric devices, you are basically taking advantage from the different transport properties of electrons and holes. So in the legs of these, for example, the usual thermoelectric junctions, you are getting the electrochemical potential difference, which you convert, which leads to the voltage difference, because of the transport behaviors of electrons and holes are different in two legs. So we did a different thing. We took the same material and the same charge carriers for the both legs. So if you do that, you wouldn't get any thermoelectric effects because the electrochemical potential gradients will be different. They will be the same in the both sides of the junction. But here, due to the shape difference, transport properties of the particles also change. This is a demonstration of that. So when you calculate the electrical conductivity, thermal conductivity, Seebeck coefficient, for example, this is the Seebeck coefficient at different temperatures and different degree angles, you see that it is different, especially in the non-degenerate regime. So this non-degenerate and weakly degenerate is coming from the semiconductor terminology. Do not confuse with the energy degeneracy. Yeah, so the shape difference actually leads to the difference in the transport properties of these materials. And that you can harvest, you can take advantage in thermoelectrics. And surprisingly, initially we thought this effect would be very small because in the end, this is a shape effect, but the bulk effects are usually much higher, right? But it turns out that the effect is not really that small at all. You can get millivolts, you can get the voltage in the order of millivolts. Of course, this depends on many things, the temperature difference, the temperatures of the junctions, and the sizes of the junctions, of course. But at least we have chosen some parameters which are in line with the current technology capabilities. And this is the voltage result we got. So we offer this as a new way of, it's a new degree of freedom that you can manipulate in thermoelectric devices. Of course, there are issues about like how we achieve these, like how we induce these shape changes. That's basically an engineering challenge, but this serves as a proof of concept that it is doable. And okay, the applications are not confined into these two examples. Right now, I'm working on several applications of this. One is on the Josephson junctions. There can be more applications in some other areas. So if I can have more students, it would be great so that we can explore more applications. Or of course, I am open to the collaborations anytime. Okay, let's wrap up things. So here I introduced you a new type of geometric technique, which is called size-invariant shape transformation. And it changes the spectra in a non-trivial way. It induces non-uniform level scaling. And once you combine it with the statistical mechanical approach, the thermal states, you reach the quantum shape effects and quantum thermal avalanche effect. And this changes the physical properties. Here I showed you the thermodynamic and transport properties, but in principle, it changes any other physical property because this effect is so general. So the take-home messages are this non-uniform level scaling causes non-trivial changes. It could be important in several other areas. And I told you that entropy behaves weirdly, so it really leads to some interesting devices. And I want to emphasize that what we have done here is very general. So we are basically changing the spectrum of the Schrödinger equation. So give me some Hamiltonian. If you can induce this effect, it will behave the same. It will have very similar behaviors. So in that sense, I think this could be applied to many other systems. So very small advertisements. I have one master's student position available, fully paid, with also accommodation and everything. And in the future, there will be openings for PhD students and postdocs as well via the projects that I'm applying right now. Last thing is this some kind of an outreach effort that we were doing with the colleagues at Harvard. So I was working with, I'm still working with Eric Heller there. He has an amazing way of visualizing scientific ideas. So for example, here you see on the left top, this is a branched flow. And it really becomes, when you manipulate it in some ways, it becomes like this in the right middle one, and so on. So these are really cool things that we have discovered while doing some numerical studies and so on. So we decided to expose them into the public and also explain the idea behind them, like how we get there, what is the physics behind it, and so on. So there are like educational content as well in this website. There are interactive animations, and you don't necessarily need to be a physicist to understand them because we were trying to explain it also in layman terms. So feel free to check it out. It's really nice pictures that we produced. And thanks for your attention.
Thank you so much. I clap for everyone. Feel free to throw your emojis. Thanks a lot, Alhun. So now we have time for a few questions. Since we are not so much, I guess anyone can just unmute and ask question. Maybe I will just quickly start to be sure that I understand and to leave time for people. By the way, if you are shy to speak, you can also write your question and I will read them out loud. But I just want to ask, in your thermal machine, if I wanted to reproduce what was on your slide with the Stirling-like, yes, this one, Stirling-like cycle. If I wanted to reproduce that with in an experiment, what would I need to put in this gray box in the middle?
Okay, great. So it could be something like a core shell nanostructure. So the core one is this gray thing, which is basically, you can think of it as an insulator, where you don't interested in the behaviors of electrons there. And you can think of the other one as your real material, the shell material, where you are manipulating the behavior of the electrons inside. So the core shell structures are perfect, I think, for this. But of course, the drawback on these core shell structures is it's really hard to continuously orient the core part. That's the challenge, I think.
I see. Thanks. I see Shen has a hand raised.
Hello, can you hear
Hi.
me? Hi.
Yeah.
Thank you so much. Lower my hand. Thank you so much for this talk. I found it really interesting, and I was especially really excited because I actually studied a really similar problem for my master's, and we actually found so we considered a domain like that as well, and we were looking at a one-dimensional domain, and you were also changing the shape of the domain over time adiabatically. But what we found was that you get this cascading effect as well, but it's not a cascading towards the ground state. It's a cascading away from the ground state, and there are results in the literature that say that you get an exponential increase in the energy spectrum. You get an exponential climb up the energy spectrum. What I wanted to ask was, could you just sort of elaborate more on the, you said that you get an avoided crossing. Now, in order to be able to actually apply the adiabatic theory and to sort of use those results, you have to sort of, the trick is you decouple your space periodically so that you can say you've got, you know, eigenfunctions of one space and you've got eigenfunctions of the other space. And you know, I can apply the adiabatic theory separately, and even though you get a crossing of the spectrum, that doesn't matter.
Mm-hmm.
I was wondering why, so I don't think you're exactly doing that in this setup. So
No,
why,
yeah.
like,
So,
why do you get avoided crossing then? I'm a bit confused about that.
yeah.
And also, oh yeah, I've got so many questions, but I can start off with that.
Okay, first of all, let me start with the effect that you told about, like increase in the, I mean, getting away from the ground state.
Yeah.
What I'm thinking, if I really didn't understand whether you are doing the exact same operation or not, but if you are doing very similar operation that I introduced here, then maybe you are going not from here to here, but in the reverse direction, right? So
If you're rotating, does it? So if you're
for example,
rotating, would it?
in this rotation,
Right.
if you start from 45 degree and try to reach to the
Right.
0 degree configuration, then you would get the same effect that you described.
Oh, okay.
So maybe the direction is different. So that's what I try to explain in the first place. Like, I choose here the direction in the direction of increasing quantum shape effects.
Yeah.
But of course, I need to define how quantum shape effects increase in that direction. But I think that would take a lot of time. That's why I skipped that.
I see. Yeah, no, we were doing a periodic thing. So you were actually spinning it round and round and round. And
Oh,
what
I
you'd
see.
expect from the adiabatic theory, that you'd end up back at the energy level. So you wouldn't expect anything interesting happening. But because you decouple your space periodically, you get really interesting dynamics. So that's how it differs.
Okay, there are differences between what you consider and what I consider here. Then also, when you say adiabatic, so here we are doing things quasistatically.
Mm-hmm.
That's different from adiabatic changes in some sense, right? So here everything is infinitely slow and in thermal equilibrium. So you wouldn't expect the same things that you would expect from adiabatic transition, for example.
What's the difference? What's the difference with adiabatic? If you're assuming that you have an adiabatic evolution, then it's really slowly, and so the adiabatic theorem applies, and you don't have.
Are you thinking quantum
transitions.
adiabatic? Quantum adiabatic?
Yeah.
Yeah, but
Yeah.
then there could be differences. For example, like you might not be able to assign the same temperature to the different states, right? So here, the states have exactly the same temperature. For example, when you try to do that adiabatically, you need to preserve the occupation probability is the same while doing this change, but you can't really do that in quasistatic change, as you might see. For example, where was it? Do I have it here? No, I guess I don't have it, but like, for example, the thermal probabilities can also shift or change during this transition. But in adiabatic, quantum adiabatic case, the probabilities also should remain constant as far as I remember. But
so the adiabatic allows you to follow the spectrum. So, you know, the dashed line that you have, for instance, that would, for us at least, that would be due to the adiabatic theorem.
Mm-hmm. Yeah, I think there are differences, but let me explain the avoided crossing part here.
Yeah.
So if you would do this, okay, here, for example, I'm thinking of these two systems as like, you can think of it like this. I first solve the Schrödinger equation for the left part, independently for the right part, and I get the union of the spectra. You would get exactly the same effect.
That's what we did too, yeah.
Yes, but you don't need to do that. That's what I'm saying. So it could be the same domain, the same domain, and you here, instead of Dirichlet boundary conditions, you could have finite boundary. Or let's ignore this one. Let's consider, for example, let me go to the backup slides. This one. Let's check, for example, this type of operation. Here, it's more like a continuous, really avoided crossings you can define here. For example, the spectra of this system, you don't have to decouple and get the union. So it's already one spectra you have. And here you see this is K, the momentum values, and this is S is the position change. You see here the real avoided crossings in the spectra. So these are really, if you would do this, let's go back to the previous example. For example, here, where is it? Here, the first excited state, really, initially you would expect this to follow this path upwards, but it really acquires the behavior of the other one here, the third excited state, and this is the avoided crossing, exactly what we define it like that. But this is an infinitesimal avoided crossing, so there is really a crossing kind of behavior here. The reason is this is a Dirichlet bound. This is the ideal case. If you would do this for a unique spectrum, for a single spectrum with, let's say, finite boundaries, you would have the real avoided crossing. It will come like this. Without touching it, it will go down.
So you've got a spectral gap.
You will get a spectral gap, yes. But here we don't have it, because this is an ideal system. You can't construct this system in real life, right? It's really separate systems. Then you combine it.
Right. I see. Yeah.
Right.
I don't want to take up all the time, so.
Yeah, we can come back and continue the discussion, but there are other questions. Maybe I see a hand raised by Alessandro.
Nice. Thank you for the nice, very interesting talk. And just wondering concerning your idea to use this in the Josephson junction, because if I get correctly, I mean, the idea is that the phase difference is okay, change the energy of the underbound state that in the Josephson junction determine essentially the Josephson energy. And in the end of the story, that give you a sort of way to reproduce this at the level of, let's say, superconducting junction system. To be honest, we I'm talking you from Pisa, and we have done it. I mean, we have computed exactly for this case where you look the phase difference as a sort of way to manipulate the energy of the Josephson junction and make a thermodynamic cycle with it. So this is okay. So, or maybe I am wrong. Or can you explain better what you think about Josephson junction?
No, actually, I was thinking exactly the same. In order to get a measurable difference, though, the Josephson junction would be at very low temperature, or the sizes would be very small. But I would think that you would get a measurable difference between that.
Yeah, sure. You can do. I mean, we have not done experiment actually because.
Oh, great! I didn't know that.
No, we have not done experiment.
Can you send me the article?
Yeah, sure. I will send you. I mean, but the point is that the energy, the real issue is the fact that it's a really complex. The Josephson junction. I mean, typically when you do an analysis, we simplify it in a certain sense, and instead it's a complex system because it's an interaction between the two sides of the junction, and so you have to take in account of the let's say feedback effect from the junction on the lead, and this okay, to compute all these things in a realistic way. It's not easy. You need to use the equation and diffusive approach. And by the way, the effect is anyway very small. So essentially, you can do cycle and so on, but the type of changing that you get is extremely small. Okay, even if the temperature is very low, even if the energy scale goes down, the effect is very small. Okay, so in a certain sense, indeed, I don't know if we will ever try to do the real experiment because it's crazy low. But anyway, the theory is done. It's very complete.
I see. It's good to know that. So what I had in mind is actually taking advantage from this low entropy behavior. I was thinking, since that is connected to the fluctuations in the system, I was thinking maybe if I could reduce the effect of fluctuations by tuning the system into a lower energy, into the lower entropy state, so that I could have, for example, longer coherence times, maybe, possibly, and so on. That is the idea that I'm thinking.
Okay, but we can discuss. I will send you the paper.
That would be great.
Okay.
Thank you.
Thank you.
Nice. There is a question in the chat by Carl Andreas Pelka. Thank you so much for the interesting talk. You said that you observe lower ground state energy with the increase of quantum shape effects. Is this a general statement that can be proven?
It is. In the direction of increasing quantum shape effects, let's re-emphasize that, the direction. The effect of lowering the ground state is can be mathematically shown that it is there, and actually, okay, not in a rigorous proof-wise thing, but in this paper, I am demonstrating that. Again, I'm not a mathematician. I'm not mathematically proving that, but once you read this article, I think you will see why.
Thank you. Okay, does anyone want to ask a question? Rob, maybe.
Yeah. So I guess it's on the slide where you showed your cycle for your machine. There was, so I guess I want to understand a bit better the step at the top going from 2 to 3, where you say it absorbs work, but it also absorbs heat.
Mm-hmm.
Because if I just think, if I have a bunch of energy levels and they move when you turn the central region. So if I just look energy level by energy level, if it moves up in energy, then if it's occupied, you need to absorb some work to move it up in energy.
Mm-hmm.
But then if it's coupled to a reservoir, I would expect that because it then wants to re-establish a thermal distribution, it will then radiate heat into the reservoir to re-establish a thermal distribution at 300 Kelvin, for example. So it seemed to me like if I think about just one energy level moving up or down, you always get the work and the heat are opposite. So I'm a bit confused about how they can be the same, or in the same direction, let's say. It can absorb heat and work at the same time.
So that's actually, you can trace this behavior into the behavior of entropy. So it exactly comes from the decrease of entropy, actually. If you look at how they behave, normally what you said would be true exactly when free energy and entropy behaves oppositely. Because in that case, you are basically, from 2 to 3, we are going from 45 to 0-degree configuration. So we are giving work to the system. So we are overcoming this free energy barrier. And also we are giving heat to the environment. The system gives heat to the environment. In the case of entropy would increase. But as you see here, these behaviors are not opposite, but the same. So this leads to such a same sign energy exchange. And also you can think of it this way. So we are not, so ideal gas relation is broken here. This system do not obey the ideal gas law. So when I'm moving from 2 to 3, I'm giving work to the system, and it's more confined right now, effectively at least. In this 0-degree configuration, it's more confined. But also the energy levels, the populations are distributed in such a way that the entropy is also higher. So normally it would be the opposite, but again, this is due to the weird behavior of entropy, and there is this competition actually between the classical behaviors and the quantum thermal avalanche effect that I just described to you. So in one hand, the system becomes more confined from here to here when you go that, but also energy levels, the distribution of the energy levels become change in such a delicate way to induce some opposite behavior. I don't know if that becomes more confusing or not, but
yeah, no, okay, so I see the point, but I guess I don't have a microscopic vision of it. If you show, for example, your plot of the energy levels, how they change with the separation, but yeah, exactly, yeah, something like that. So I guess you could make a similar plot as the one on the left here of the eigenvalues as you in the square as you turn the central square.
Mm-hmm.
And then I get, okay, then I guess now it's an open question. If you don't have the answer, is there a way to see how this heat flow and energy flow can be in the same direction in terms of the occupation of these energy levels, that you just take 2 or 3 energy levels and you see how because sort of naively you'd think that it would be in the opposite direction.
Yeah, the confinement. Yeah. So it's about the here when you. Yeah. Okay, let's go back to here. No, the cycle. So when you do this operation, you are inducing more confinement energy into the system. So it becomes effectively more confined. And that increases the internal energy so much. So that actually compensates this work and heat behaviors. In the end, it's the first law of thermodynamics, right? So you need to get but it would be much more clear if I, for example, rather than just entropy per state here, if I plot the free energy per state and internal energy per state, you can clearly see how each energy state contributes to three quantities that are in question. And there you can see how it leads to this behavior. I just focused here on entropy because that is the most like a dramatically different one. But yeah, the answer lies here actually.
Okay, thank you.
Well, thank you, everyone. I guess we will stop the recording now. We can still stay a bit more for informal discussion if you want.